Hi all, just checking the microphone's working. Good morning, my name's Lawson. I work for Red Hat. I am a developer advocate. Prior to Red Hat, about 13 years ago, I used to work for a living. I was a software engineer for the government for about 20 years, working on AI and big data sets. I come from an AI background. I did a PhD in artificial intelligence, and I have been trying to write for the last 7 years an AI. And I've had a huge amount of problems with writing this AI because the technology just hasn't been there to do it. And then suddenly someone nicely invented Knative Serverless. So what we're going to talk about today is basically the concepts of Knative Serverless, and I'll explain exactly what it is, how you use it, what the different mechanisms are within it. And I'm going to talk about the approaches in terms of next generation artificial intelligence applications. Now, it sounds boring, and it isn't, but before we start, I want to talk about artificial unintelligence for a second. Everybody nowadays is talking about AI. Literally everybody. And there's a part of me that thinks, yeah, that's fantastic. And there's a part of me that thinks, for God's sake, please stop talking about artificial intelligence when it's not artificial intelligence. You know, when I grew up, those were my versions of artificial intelligence. It was HAL from Space Odyssey. It was the Terminator. It was Colossus, for anyone who's seen that fantastic film from the 1970s. All these sort of massive sort of brain things that were going on. But seriously, and this is where it gets a bit philosophical for a second. Piece of source code there, okay? I've got int first number equals, what is it? 20, int second number equals 15. And I'm doing system.out.println. I have discovered that first number plus second number equals first number plus second number, exclamation mark. Is that artificial intelligence? Because to me, that isn't artificial intelligence. That's just programs. That's rule set definitions. When you talk about ChatGPT and all these kind of things that are very, very trendy at the moment, they are just plagiarism engines. They're looking at massive data sets. They're looking for patterns within that data set. I had to strip 4 or 5 slides out of here because it's being recorded and there were swear words. I do a very nice thing, a couple of slides which I've taken out, where I do a comparison of Jane Austen's novels to a novel that I wrote. And I can put all of Jane Austen's novels into a ChatGPT style AI algorithm. And I can generate what's called n-grams to do definitions of design patterns within it. And I can compare other Jane Austen books and see that they're within 90 to 95% similar. I can compare my book and it's 45% similar. But that's not artificial intelligence. That's just clever algorithms. So what I've been thinking about recently, I say it's been about 7 years, is this concept of design versus evolution. So you've got what are called genetics, and genetics are basically rule sets. This is what you're told is true from the start. You can't change your base rules. You've then got something called mimetics, and this comes from an idea that Richard Dawkins came up in one of his less controversial books. And they're the evolution of rules that you were given to start with. They are rules that you build from experiences. And most pure AI systems start with a genetic rule base and build a set of mimetic rules based on external influences. And that's a good way to start. It's not the kind of ChatGPT approach. So what I've got from a next generation AI thought, and I say just give me a couple of minutes and I'll get onto Kubernetes. This kind of engine would have atomic level components like neurons. And this is where we're going to start to talk about Knative Serverless. When you're building an artificial intelligence, you want to break down the actual knowledge in the artificial intelligence down to the most atomic points, the most atomic operations. And you get the artificial intelligence, and you get the kind of complexity of the system by combining these together. And in the old days, this was incredibly hard to do. You know, you had to use Hadoop lakes and HPC and all this kind of stuff. But we've now got technology that allows for hooking these components together quickly, efficiently, and encouraging atomic decomposition of functionality. So let's talk about Knative. So, definition of Knative from the source project site. Knative is an open source enterprise level solution to build serverless and event-driven applications. In actuality, it's 2 things. One is Knative serving, which is a fantastic way of actually scaling your applications down to 0. Again, I normally get told off when I'm talking to customers and interested parties about this, because I get very upset with the terminology serverless. Because it's always someone else's server. And I used to refer to it as the unicorn's arse until salespeople told me to stop doing that. The Knative serving simply allows you to scale down an application to 0 replicas. And you can already do that with a deployment. You can do it with on the Kubernetes side. But if you actually scale a Kubernetes deployment down to 0, the service ingress point remains. So if you send traffic to that service ingress point, you get an error. You get something like an NGINX or an HA proxy formatted application is not running and all these kind of things. What Knative serving does is it produces a resident service endpoint, but it still scales the application down to 0. What that means in English is the application goes away, it doesn't consume system resources, but the actual ingress point is still there. And when traffic ingresses into the ingress point, the application is restarted instantaneously. And that's the beauty of it. Now, again, I get told off by salesmen because it means you have to buy smaller clusters. You don't have to buy as many nodes because you can get massive amount of these Knative serving services on a node because they don't consume any resources. And for those who know the algorithms for the node placement within Kubernetes, the actual Knative serving services do not contribute to the totals for node placement. So when you're placing the applications itself, you can put these applications anywhere because they have 0 resources when they're not being used. The advantage is when they scale up, and if they scale up to the point that the node is being overloaded, they can be rescheduled and moved to other nodes. So it's this wonderful way of being able to stand up, let's say, an application that's made up of 500 microservices as 500 individual serving components and have them consuming no resources. It's a green way of doing it. The other component that's part of Knative is, to me, the slightly more exciting one. That's Knative eventing. And what Knative eventing gives you is a number of API endpoints to build event meshes. And when we talk about event meshes, it's basically the way of redirecting events around the system, but tying them into the Knative serving services. So all of your endpoints, instead of being driven by traffic arriving into the service point, they are driven by an event being driven around the system. And I'll talk about that in a moment, about how that's actually done. So the Knative serving basics, what it does is when you add the operator for Knative, it actually extends it with 4 CRDs. And unfortunately, I wish people stop doing this, we have overloaded terms. So you've got basically what's called a Knative service. So you've got a Kubernetes service object, and you've now got a Knative service object. What that service object actually defines is the state of the application that you want. So basically, it defines the state of the application and the way that application behaves in terms of 0 replicas, how it spins up. One thing I'll talk about in a second is you can do actual auto-scaling of the application replicas based on the throughput traffic, which is really nice. But what that actually has under the covers is 2 main objects. One's called a root, and one is called a configuration. The configuration defines the exact specification for the application, but it's singular. So when we talk about the actual definition of the configuration of the application, it's things like environment variables, it's things like what config maps, what secrets, all those kind of things that make up the deployment itself. But it is a singular object. And what happens is, when you actually deploy one of these things, and when it spins up, it creates what's called a revision. And a revision is an immutable instance of the configuration. And it confused the hell out of me when I first started using this. So if you change, for example, the environment variables into that service, or you add, let's say, a config map, or you change the specification of the application itself, it will generate another revision. It updates the configuration is singular, and it generates another revision. The nice thing about Knative serving as well is that you can use the root to actually push traffic to multiple revisions. So if you've got 3 versions of your application, you could say 30% of the traffic goes to the original one, 30% goes to the second one, and 40% goes to the newest one. So it allows you to do canary deployments and blue-green deployments as well with these kind of things. The mechanics are really simple, and that's what I love about this. It's a complicated little beast, but the mechanics that underpin it are extremely simple. A Knative serving application initially deploys without traffic, giving the settings defined in the configuration. So when you actually create a Knative service, it will deploy the application and it will actually spin it up. So a pod will appear, or X pods, depending upon the replica count that you want. It then starts a timeout going. If no traffic arrives in the service point during that timeout, When the timeout expires, the application is scaled down to 0, but this ingress service point remains. If traffic arrives in that service point during the timeout is reset. So it's got this wonderful way, and that timeout is fully configurable as well. So when traffic arrives at the route, it is forwarded appropriately to the revisions. In the case of one revision, for instance, this defaults to 100% traffic. If the application is scaled down to 0 replicas when traffic arrives, it is scaled back up according to the behavior stated in the configuration. And the configuration could define whether it spins up to 1 replica, whether it spins up to 5 replicas. It can also define the network traffic thresholds. So it's got the ability to say that each individual replica can have 10 concurrent connections. If it has more than 10 concurrent connections, it will spin up another pod. And it also has requests per second, so you can do a combination of the number of concurrent requests going into your application and the number of requests per second that are being processed. That's the auto-scaling stuff I just talked about. It can be done via concurrency, it can be done via requests per second. It's nice because you can use horizontal pod autoscaling to scale your applications based on system resource consumption. But you can't use an HPA to actually spin up additional things based on the network traffic. If you're using Knative Services, you can use HPA to actually do system resource-based scaling, but also use this for network traffic-based scaling. On the eventing side, I really love eventing. And the reason I love eventing is I spent too much of my life writing message-based systems. And I always talk about the 70-30 code split. So as a developer, when you're working, writing some code, in the old days specifically, 70% of your time you weren't writing code. You were downloading patches, you were installing frameworks, you were writing boilerplate code. I can go to sleep at night, and the instant before I go to sleep at night, I can write an Oracle connection string. I don't want to, but I spent so many years doing it. And the reason I'm talking about this is that what we've done with Knative Eventing is we produce this concept called a cloud event. And a cloud event is an abstract event. And when you're writing the actual Knative Eventing and you're consuming these, the cloud event itself is incredibly simple. You don't have to worry about the transport protocols, the mechanisms of decryption, and all those kind of things. It's all done for you under the covers. And this is when we get into where we start to talk about the eventing side of the Knative services, where you can actually drive the creation of the services by events rather than traffic. So eventing versus serving. Eventing is a set of extras that allow for the engineering of event-driven architecture applications. And it has this concept pop back here very quickly. So eventing is a set of APIs for routing events from producers to consumers. Consumers are also known as sinks. And what you can do is you can actually have Knative serving applications acting as sinks, receivers of those cloud events. What's really nice, and I'll show you in the demo itself, is that these actual Knative serving applications can emit events themselves. So I'm a lot older than I look, so I'm used to actually writing HTTP protocols and playing around with those kind of things. Under the covers, a cloud event is a post. And that's all it is. And it's got 3 pieces of metadata. It's got an ID, a source, and a type. And the ID and the source are basically a combinatorial UUID for the actual event within the cluster itself. And the type defines what physical type that event is. And what Knative Serving uses is it uses things called triggers to push events of certain types to certain Knative Serving endpoints. Very quickly on the cloud event side, as I said, there are 3 pieces of metadata. ID, unique identifier for the event. Source is a textual representation of the producer. And the system as a whole treats those two as an aggregated UUID. What I mean by that is you have this concept called a broker, which you throw the events into. If it has already seen an event with a combination of that ID and that source, it won't resend it. That's already been seen and it's been processed. And type is effectively the target for the cloud event. Very quickly on the brokers and triggers side. At its simplest, eventing provides the concept of brokers and triggers. They're both native objects, native Kubernetes objects created via CRD. The brokers are basically the point of ingress for the events themselves, and we'll talk about those a little bit in the demo. Triggers are where it gets clever. So trigger allows you to tie a cloud event type to a service endpoint. So a broker sits there with a set of triggers, and when it receives an event, it gets the type from the actual event, and it processes all the actual triggers to see which ones it has to push it down the line to. There are some extensions in Knative Eventing using channels and subscriptions for doing multicast and all these kind of things. But to put it simply, you push an event into the broker then forwards that event onto a sink, which can be a Knative serving endpoint. So, let's talk about an example of this. And this is based on the stuff that I've been trying to write for 7 years. I've been trying to create basically a neural net. And I want this neural net to be made up of atomic components called neurons. So I've called it K-neural. So K-neural is an idea to build an adaptive artificial intelligence for a number of small atomic Knative hosted event-driven components, which I call K-neurons. Each component is stateless. And this is the beauty of it. So when it actually fires up, when the application starts, it uses a provided ID to go and get its memory state from a data grid. And this is the beauty of it. So it gets the memory from the data grid, it processes it based on the information that it's got, the information it's been given, and the rule set it's actually processing. It will then emit events if certain thresholds are exceeded or not exceeded, and then it puts its state back into the data grid. So when the application scales down to 0, it's gone, but its memory remains. The nice way of doing it this way is that the neurons themselves are completely stateless. They get their memory state from the data grid, and you can actually inject the rules and the threshold information directly into them. So you could have this system running with a single neuron. You could have it running with 5,000 neurons. The limitation is basically on how complex you want the adaptive artificial intelligence to be at the end of the day. And I say, well, the way I've done it is I've got a broker that actually pushes events of certain types using triggers, which trigger K-neurons, which pull their memory state from a data grid and push it back to the data grid itself. And it's a small, pithy example, but it's highly scalable because you're breaking down the functionality of what your neurons do into the smallest atomic components. So rather than writing a big sort of chunky machine that drags in data and just chomps through it, you have these little things that just pop up when needed and go away when they're not needed. So it's highly efficient. So I've got a demo. There's also a blatant Red Hat plug there with loads of freebies if you want it. I was told to put it on the deck, which I did 5 minutes before I started this talk. There's actually some really good downloadable free ebooks. They're on Kubernetes patterns. And other things. And I'll come back to that slide after I show you the demo. So I'm not sure how much of that you can see, so I'll scale in a little bit. I'll explain the components before I scale in. So what my project has got in it is it's got a stateful set of components. And those stateful set of components, you can see one of them is actually this one here. One of them is actually a cloud emitter, and it is a Knative service, so it's currently scaled down to 0. That actually generates a node app, which looks like this. If I show you. Apologies, I haven't written a style sheet since 1996. And this allows me to actually create and mold an event and push it into the broker itself. As you can see from the topology definition, that's actually currently scaled down to 0. I've also got two other things which remain resident the entire time. One is called Grid Connect, and that is basically an API engine I've got that does the memory storage. I'm actually using Infinispan, so it's an in-memory Java data grid. But in order to abstract the applications away from the way in which the data is being stored, I've got a resident point. So all my little neurons talk to that Grid Connect, and they send very simple sort of get and fetches. The Grid Connect itself contains the state of the endpoint in terms of the in-memory data grid. And the other one's something called Watchman. And Watchman is something I came up with because if you know when you scale an application down to Kubernetes in 0, the logs disappear. It's one of the problems we've got. You scale down to 0, you can't see what the application's doing. And when you use Knative serving, these things come into existence, they process what they need to do, they finish. After the timeout, they are removed. At that point, they don't have any logs. So I've got basically a resident system that allows the K-neurons to log information about what they're doing. And that's my stateful part of the system. This bit here, in the middle, is my neural net. And it's a small neural net. I'll just zoom in so you can see it a little bit better. So what it is basically 3 neurons. And these neurons are actually being driven by Knative events. Those lines you see up here are actually triggers. So I've got a broker within the system, and the broker is just the marshalling point for events. That broker has 3 triggers currently attached. It's actually got 5, but I'll explain what the other 2 are. So the 3 triggers are basically, there's trigger test 1, trigger test 2, and trigger test 3, which are different event types to trigger different instances of the neurons. So you've got 3 neurons. I've actually got, as well, 2 endpoints here. And they were written in Camel-k. So Camel-k allows me to write a Knative event consumer in 1 line of Java, which makes it incredibly easy to write these things to test. And all those endpoints do is they respond to the neurons generating a high threshold or a low threshold. So how the neurons actually work is they've got a state, which is a number, which is stored in the memory grid. And I can send events into them, and the events are actually targeted to individual neurons, and the events can have addition, subtraction, multiplication, and division, and a number. And that's applied to the state that the actual neuron gets from the grid. If that state exceeds an environment variable, which is the high threshold, the neuron will emit a high event. If it falls beneath a low threshold, the neuron will emit a low event. And those 2 endpoints written in Camel-k are just, one is to actually consume high events, one is to consume low events. It's a very simple kind of concept, very simple kind of setup. So very quickly, what I'm going to show you, and I'll make this slightly bigger so you can see it. You can refer to the brokers as an endpoint. So, for example, my broker is called default, and it lives in my namespace serverless demo. So the endpoint for the broker is actually just the cluster address with the local thing. You can, if you're doing it locally, you can use .svc.cluster.local and things like that. I'm going to pass in an event of type test event 2, and my payload, the operator is addition, and the value is 10,000. So what this is going to do is it's going to drop an event into the broker. The broker is going to spin off kneuron 2, which is actually linked to test event 2, pass that payload in. That neuron's going to get its state from the data grid. It's going to add 10,000 to it, and if that exceeds its threshold, which is set to 1,000, it will emit a high event. So just to show how it actually works, I'll just emit the event and then pop back. And what you'll see down here is my emitter fires up, the broker gets the event, my neuron fires up. It's detected if we go into it and look at the logs, but the threshold's been exceeded. So what it's done is it's pushed a high event back into the broker. The broker's gone through its triggers for what actually has to deal with a high event and passed it off to my Camel-k. So you can see what you've got immediately is a distributed system that's incredibly efficient. Because I'm going to walk up and down and talk for a minute or so, and while I'm doing that, the timeouts on all of those Knative services will expire. And what it will do is it will actually scale those applications down to 0. Now, the advantage of that from a consumption perspective is that whilst these things are not running, the cluster has minimum resource consumption. And you can scale your cluster down to 1 node. When you're thrashing this, 10,000, 20,000 of these things running, you can upscale your nodes. So it's a very efficient way of doing things. What I love about it most is that you can start to introduce some serious complexity in the artificial intelligence just by putting these things together like Lego bricks. So my eventual intention, I've been working on this artificial intelligence for 7 years called the thought engine. I'm going to build the whole thought engine in K-neurons and actually deploy it like this. So how are we doing for time? 5 minutes. Any questions on that? It's a lot of information. Anyone? Yes, thank you. Yeah. Right, the question was, is there a overhead on the system in terms of latency when you spin up and spin down the actual pods themselves? One of the things you would have noticed, or you wouldn't have noticed, I actually didn't show you, but when you actually create these things the first time they spin up. So one of the things we actually suggest when you're doing this is that you spin up the Knative service initially with the number of nodes you've got. And what that means is the image gets distributed to all the nodes. So it spins up once without traffic, and then it shuts itself down. When it gets called again, it's instantaneously recreated because the image already exists on the worker node. You can actually create it, you don't have to do that. You can create one instance, and then, let's say if you've got 10 worker nodes, the first 9 people will get a bit of a pause while it starts up. But once it's already physically started on that node, it can restart instantaneously. And a quick aside in terms of technologies. I'm a Java guy. I've been using Java since 1996. I love Java to pieces. I know it's got a bad rep. But we've got this new thing called Quarkus. And what Quarkus does is it allows you to recompile Java in such a way that it starts up incredibly fast. I won't bore people with it because it's all about the way it pre-processes the class loader and the class definitions. But long story short, if you're using, let's say, Spring Boot for an application, you can write a Spring Boot application, you can compile it using the Quarkus engine, then you can put it in Knative Serverless, and it'll start in microseconds. And this is a standard Spring Boot application that normally starts in 40 seconds. So there are ways and means to architect this and ways and means to engineer this. As I say, the initial sort of statement we say is that have an initial count of your deployment to match the number of worker nodes, and you're guaranteed that that image is going to be deployed to every single one of the worker nodes. That make sense? Yes?
How can this be called AI?
So that's a good question. That's a good question. This implementation itself is not artificial intelligence. Sorry?
Can you repeat the question for people who aren't?
Oh, yeah. How can this be called an AI? This is not an AI. This is a very, very basic indication of what you can do with K neurons. What I'm intending to do with my actual artificial intelligence is the thought engine is working on memes. So it has a base knowledge of the universe in terms of objects. So it doesn't have to, you don't give it real English, you don't talk about those kind of things. Is that me? What I'm going to do eventually is have the concept of the data grid holding the memory state of the entire system, and the application and the changes of the rules that are used within the system being actually within the neurons themselves. So at the moment, for example, these neurons, you pass a value into it, you pass an additive or subtractive, and it just adds and subtracts. But what I want to do eventually is pass code into the neuron. So the code will get an initial base state and a code rule set. And then what I'm going to do is I'm going to use the neurons and something called what's the one? My brain's gone dead. I did my PhD on it, and I can't remember what it's called now. Learner classifier system. It's going to use a learner classifier system to generate new rule sets based on the existing rule sets from the memory state, and then trial them out. Compare them to a health factor that's dependent upon going to other neurons and firing it in, see what the neurons do, build a kind of adaptive response to it, and then it will build additional neurons based on these new rules that it's created through genetic mutations on the actual source itself, and then it will cull the rules that are least healthy at the endpoint. So that's the idea behind it eventually, but if I did that, then you would not be able to read the page at the moment. I think I've got a minute left. Any more questions? I'll bring that back up, that slide for the freebies. Again, thank you for that. That was about 8 hours of information in 30 minutes, which is why I was talking pretty quickly. If anyone wants any more info, feel free to give me a shout. I personally think Knative is the best thing since sliced bread. The other thing I would say about it is that I've also been looking, has anyone heard of Argo CD? Yeah. So I've been basically using Argo CD to predefine the Knative services. So if anyone's interested at some point, give me a shout. I've got a GitHub repo that's got the full definition in Argo CD, customized files for actually setting up these demos and running this kind of stuff without going through the 450 steps I had to do to get this demo running this morning. Cool. Is that it? We good?
Okay, thank you very much.